Hello, good day. Today we would like to talk about the basic of electromagnetism transformer. It is under FEP 101, Basic Electrical Technology. Yeah, the contents are included magnetic field, electromagnetic induction, force on a current carrying conductor, Faraday's law, Lenz's law, Fleming's right-hand rules, induced EMF, flux density, permeability, reluctance, Ohm's law for magnetic circuit, series magnetic circuit, ideal transformer, transformer efficiency, and a current transformer. So why we study electromagnetism or electromagnetics? Electromagnetics is the fundamental to the advancement of electrical and computer engineering technology. So electromagnetics is used to generate electricity, store memory on our computers, generate pictures on a television screen, diagnose illnesses. Examples of this, for example, the 4G, 5G communication technology, all that involve electromagnetic wave. We have a CCTV. This is some sort like iPod, telephone, monitor. So definition of electromagnetism. Electromagnetism is the branch of science. It is electromagnetism is a science, branch of science that concerns the forces that occurs between the electrical charged particles. So when we talk about electromagnetism, it is a science actually. Then what is involved? It is involved force. It involves the force that generated by the electrical charge particle. So in electromagnetic theory, these forces are explained using electromagnetic field. So we have several magnetic materials. For example, permanent magnet. It is a magnetic material that can retain its magnetic characteristic. So for example, a mixture of aluminum, nickel, cobalt, and iron. We have also a temporary magnet, a material that has a magnetic characteristic at certain conditions. For example, soft iron, iron alloy. Then the pointer of the compass is called as a permanent magnet. For example, in the compass, you like to see the north and the south. Then because it always retains its peculiar properties, it's suspended in a horizontal plane. So the Earth North Pole and the other end will be called as a South Pole. Definition of magnetic field. So magnetic field is an area surrounding a magnetic material that has the effect of magnetic force. For example, this line, all are considered as magnetic field. So it is an area. So this area surrounding a magnetic material. This is the material that has the effect of magnetic force. Which means if let's say I put something here, we can feel that the magnetic force. So this is called magnetic field. The curved chain between the pole can be seen in the figure. Curved chain like this. Actually it's this one, curved chain. Or here. So the shape and density of this change shows the magnetic condition of space or the field around a bar magnet. We call it as a magnetic flux. So this we call magnetic flux or outwards. Even though it is not enclosed, but it is called magnetic flux. So two poles dictated by direction of the fields. The lines of magnetic flux are assumed to pass through the magnet, emerge from the north pole and return to the south pole, which means the line will go to the south pole and then emerge inside the magnet, then go out again, then from the north pole, then go in again from the south pole. So opposite pole attract or align magnetic field, same poles will repel opposing magnetic field. So attracting field from north and the south, it will align and attract each other. For the poles which repel, the north and the north pole, this line will push the other line from here. Then the direction of magnetic field. Electromagnetism works on the principle that an electric current through a wire will generate a magnetic field. It's very simple. Magnetism works where when there's electric field, electric current flowing through the wire, then there will be magnetic field around it. This is called electromagnetism, where we change the electromagnetism word. We will know from itself, electromagnet. We change the electrical side to magnetic side, or we change the magnetic side to electrical side. So that's why we call electromagnetism works on the principle that an electric current. So electric current flow through the wire, it can generate the magnetic field. So in a bar magnet, the magnetic field runs from the north to the south pole as usual. In a wire, the magnetic field forms around the wire. For example, this one. When there's a current flowing through in the wire, so we will see the magnetic field surround it. For example, like this. When there's a current flowing through, then there will be a flux or field surround it. But how can we determine the value, the direction? We actually use a right-hand rules. So a method of representing the relationship between the direction of a current and magnetic flux, or the current, the direction of the magnetic current, the current and also the magnetic flux. How? We use Fleming right-hand rules. So we grab around the wire, then the current will go up, then the magnetic direction of the magnetic field created will around our fingers. So if the current is flowing towards us, it will indicate it as a dot arrow. If the current is flowing away from it, will represent by a cross, equivalent to the departing tail feathers of the arrow. Just a simple illustration, if this is an arrow, if we look from here, which means the flux is coming to us, so we will see a dot here. If we look from here, we will see the flux flowing through towards the other side, outwards from our eyes, we will see the tail of the arrow, which is cross. So right hand rules, yes, we explained before. Thumb indicates the direction of the current flow. Finger curl indicates the direction of the field. Okay, then we'll go to electromagnetic induction. Just now is a basic of electromagnetism. Now we want to study how it's related. Okay, how's the operation of the electromagnetic conversion? So electromagnetic induction is the production of an electric current across a conductor moving through a magnetic field. So just now we talked about electromagnetism. Electromagnetism is something like we want to, there's the conversion between the electrical side to magnetic side, or magnetic side to electrical side. So we call it as a there's a few forms. One of it we call it as a induction form. That's why we start from the most simple one. We start from the electromagnetic induction, where we produce the electric current when there's a conductor passing through the magnetic field. So we have electric current, we have magnetic field, and then we have a conductor. Three things. So the process of generating current in a conductor by placing the conductor in a changing magnetic field is called induction. This is called induction because there is no physical connection between the conductor and the magnet. Then the current is said to be induced in the conductor by the magnetic field. So inductions, there's no physical connection between the conductor and the, for example, this one. When the line is going up and in, cutting through the fluxes that are generated by the magnet, there will be electric current passing through. There's no physical connection between the wire and also the magnet. So that's why we call induction. So, put it in a proper way of a saying of this induction, we call it as a force on a current carrying conductor. If you still remember the previous slide, electromagnetic induction involves three things. One is electric current, one is conductor, one is magnetic field. So come back to here. One is conductor, one is current, electric, one is a force. So force actually is something like we need to cut the moving the conductor so that it can react with the magnetic field. So two permanent magnets rest on, for example, like this one. Two permanent magnets rest on the sheet of the paper. This paper we call as a G, and a steel pole pieces P. This one steel pole pieces P are added to increase the area of the magnetic field in the gap between them. Later I will show you the 2D one. And then this wire will cutting through the paper. Okay, midway between the pole piece is a wire W, passing vertically downwards through the paper G and connected through a switch to a battery. So next, for example, now if my eyes look from the top to the bottom from the top lah, so we will see this one. So N North Pole, South Pole, South Pole, South Pole, South Pole, North Pole, North Pole. Then this is just to enlarge the area of the magnetic flux. So we know that the North Pole will flow out and connect to the South Pole, right? And then this is our conductor. So if the switch is closed, this switch is closed, I mean we connect to a battery. Just now, if it is open, there's no current. If it is closed, so this will have current. So the lines of the magnetic flux distort partially surround the wire. Distort means, for example, the line should go through, but because of there's a current passing through the conductor, the line is distorted like this. It becomes bended. Distorted means bended. So the lines of the flux try to return to the shortest path between P and P. This P and P. They are trying to return to its original state. Thereby, they exert a force F urging the conductor. So now going in means this conductor having a current flow towards the paper. That's why from the arrow I flow towards to the paper. So when flowing towards the paper, we use right hand rules. The current is going inside. Then the flux will go to surrounding as a clockwise direction. Okay? When it is clockwise direction, it will distort this line. It becomes like this. And very naughtily, this line are trying to put back into their original state. So that's why what they need to do is they will exert a force, pushing this, go, hey, this fellow, go away, don't disturb my magnetic field lines, so that I can get back to my original state. So we can see a lot of fluxes here, less fluxes here. Then it will try to push down the conductor so that it becomes to this state back. Okay? That's why we call force on a current carrying conductor. So first we need to have a conductor. Second, it must have a current. Third, we will predict that it will have a force. So, well, we would like to put in equation or engineering terms. So the mechanical force exerted by the conductor always acts in a direction perpendicular to the plane of the conductor and the magnetic field direction. We call it as the direction is given by the left hand rules or left hand rules. Make sure 90 degree here, 90 degree here. So 90 degree this hand, this finger and this finger. 90 degree this finger and this finger. So how to put in a figure for this one? Mechanical force F is this one. Okay? Exerted by the conductor. So this is the conductor. Always act in the direction perpendicular, means 90 degree to the plane of the conductor and magnetic field direction. So where is the plane of the conductor and magnetic field direction? So have a look on the conductor. This is our conductor. Where is our field? This is our field. So the plane of the conductor actually is stated on the direction vector of the current. So this finger, we know that it is pointed as a current. This finger pointed as a B. So the plane of the conductor and magnetic field direction means the B and I plane. So we draw it out this one. This is the plane. So it says that left hand rule says that the force is always 90 degree to this plane. It will not go this way, go that way, but it will go to this way. So in this case, if there's a current passing through the conductor within this field, so B is this field. Direction is this one. Then there will be a force go to upwards. Okay? Then we put in the mathematics. it is force on the conductor where F equals to B times I times L. B times I times the length of the L in this area. Okay? So for example, a conductor present in a uniform magnetic field of the flux B pointing into the page. So pointing into the page, from our eyes it is a cross. Then in this case, the conductor where the current is flowing to the downwards. So the conductor itself with an L meter long and contain a current of the I ampere. So we can predict where is the force will go through. So by using a Fleming left hand rule, so now the B is go inside, the I is go downwards. So our V is go to our right. Our force will go to the right hand side. So we put it into an equation. Actually, F is a vector because it has a direction go to the right side. Equals to I is a current. The direction of the conductor L times B, direction of the magnetic flux density. So the induction of the force in a wire by a current in the presence of magnetic field is the basis of the motor action. Right? When there's a magnetic flux density, when there's a current, then we will have a force. For example, the fan, I switch on it. So there will current inject into the stator coil, which is the coil. Then from the coil, it will rotate the motor. So this is under motor action. We use this equation, Fleming's left hand rule, to calculate it. So for example, a current carrying conductor, the length is 150 cm long, is located at the right angles, right angles to a uniform magnetic field, having a density of 0.3 Tesla. Calculate the force on the conductor when the current is 200 ampere. So very easy, we apply the formula F equals to ILB sin theta equals to 200 is our current, 150 centimeter, 150 times 10 to the power minus 2 is our length, and our flux density is 0.3 Tesla, and then it is sin theta with a 90 degree. We have a 90 Newton. Another example, a conductor 150 mm long is carrying a current of a 60 amp at the right angle to the magnetic field. So a conductor, this is my conductor 150 mm long, is carrying a current of a 60 ampere at the right angle to the magnetic field. So the force on the conductor is a 3 Newton. This is my F. Calculate the density of the field. So first of all, we need to use an equation. F equals to ILB sin theta. So I have a F, which is 3 Newton. I have an I of a 60 amp. I have a length of 150 mm. But I don't have B. And I have a right angle of a sin 93. So I use a calculation. I put in the equation. Then I I get my B equals to 0.33 Tesla.